I believe this innovation carries the potential to dramatically boost the efficiency of electrical machines in the years ahead. There are obvious benefits to be gained by replacing traditional copper with carbon-based conductors in these systems. In fact, the possibility of transforming the entire industry is immense. Imagine being told that a completely new type of electric motor has been invented, one that contains not a single gram of copper or aluminum in its coils. At first glance, such a concept feels impossible. After all, metal coils have served as the backbone of electric motors for more than 100 years. Yet, a group of researchers in South Korea has successfully developed something truly revolutionary: a wiring system composed entirely of carbon. This breakthrough promises to redefine how motors are designed, assembled, and ultimately, how much they can achieve. What makes this advancement particularly striking is its measurable impact. The new carbon-based system boosts electrical conductivity by 133%, while reducing motor weight by over 80%. These figures position it as one of the most important achievements in modern material science. More importantly, this technology is not a futuristic dream locked in laboratories. It already exists, is functional, and is under active investigation by experts. Surprisingly, however, public conversation around it remains limited, even though its ability to reshape the motor industry and extend into nearly all technology powered by electricity is enormous. To grasp the weight of this breakthrough, it helps to revisit the fundamentals of how electric motors function. At their essence, nearly every electric motor, whether spinning the blades of a ceiling fan, powering the drivetrain of a Tesla, or driving the conveyor belts in a factory, depends on metal coils. These coils, most often made of copper, conduct electricity to generate magnetic fields, enabling the conversion of electrical energy into mechanical motion, or the reverse. Copper has remained the material of choice for decades because of its superb conductivity, reliability, and ease of manufacturing. Aluminum sometimes substitutes copper when weight or cost is an issue, but neither metal is perfectly suited for the evolving demands of next-generation electric systems. Both are heavy and expensive, which limits design opportunities for cutting-edge fields such as electric aircraft, drones, robotics, and wearable technology, domains where lightweight and flexible components are critical. This is precisely where the Korea Institute of Science and Technology, KIST, steps in. Scientists there have created a groundbreaking wiring material using carbon nanotubes, eliminating the reliance on copper and aluminum altogether. Nanotubes are remarkable molecular structures, ultra-thin cylinders made of carbon atoms arranged in a hexagonal lattice. Their exceptional strength-to-weight ratio recalls bold engineering ideas like the theoretical space elevator, which would require a 23,000-meter cable strong enough to bear its own weight. Steel cannot achieve this, but carbon nanostructures can. In fact, when researchers explored splitting molecules of 60 carbon atoms and reconnecting them into fibers, they produced carbon nanotubes, capable of forming strips stronger than the original structure. These nanotubes are thousands of times thinner than human hair, yet incredibly strong, flexible, and highly conductive. The KIST team advanced this material into practical use by developing a specialized fabrication process known as Lyotropic Liquid Crystal-Assisted Surface Texturing, LS. This method aligns nanotubes with remarkable precision, arranging them into usable cables. The resulting product, named Core-Sheath Composite Electric Cable, CSCEQ, differs dramatically from rigid copper wires. CSEC can bend, twist, and stretch without losing its superior electrical properties. This flexibility opens entirely new design possibilities for motors, allowing smaller, lighter, and more adaptive systems. Early prototypes built with these carbon-based coils have already shown excellent performance, pairing exceptional conductivity with drastic weight reductions. Researchers see this as the foundation of an entirely new class of motors: compact, energy-efficient machines capable of thriving in conditions where conventional motors cannot. The implications are extraordinary. In aerospace, replacing copper coils with carbon nanotube alternatives could drastically lighten propulsion systems, enhancing range and efficiency for electric aircraft and satellites. Electric vehicles, which currently depend on hundreds of kilograms of copper wiring, could become lighter, more efficient, and less costly to produce. In consumer markets, wearable medical devices and electronics might integrate flexible carbon wiring that molds to the human body, enabling advanced sensors and smart textiles. Robotics, too, could undergo a radical shift, with motors imitating the flexibility of biological muscles, capable of twisting and stretching in ways traditional machines never could. Even infrastructure on a massive scale could benefit. Power transmission systems outfitted with carbon wiring would be lighter, easier to install, and better able to withstand harsh environments. This advance is not just an incremental improvement. It represents a paradigm shift. For more than a century, the design of electric motors has revolved around rigid metal coils. While refinements in materials and engineering have optimized performance, the core structure has largely stayed the same. Carbon nanotube wiring challenges that long-standing model, offering flexibility and configurations previously unimaginable. Entirely new classes of machines could emerge as designers rethink drones, industrial robotics, and countless other systems from the ground up. Still, the road to widespread adoption is not without challenges. Manufacturing is one of the greatest obstacles. Producing nanotubes at industrial scales is costly and technically demanding. The LS alignment process, while effective, adds complexity because it requires cutting-edge facilities and high precision. This reality pushes up costs, making the technology less accessible for mass-market products at present. Another limitation is conductivity. While carbon cables already show outstanding conductivity, they have not yet surpassed copper's raw performance. Scientists are steadily closing the gap, but copper retains an edge for now. Durability presents yet another hurdle, since nanotubes, despite their strength, are vulnerable to degradation from moisture, oxidation, or high voltages unless treated with protective coatings. Finally, the environmental and health impacts of producing and disposing of nanomaterials remain uncertain, and further study is required to guarantee sustainability and safety. These obstacles help explain why the technology has not yet revolutionized the motor industry. Breakthroughs in materials science often require years, or even decades, to evolve from lab experiments to widely available consumer products. Mainstream tech news tends to spotlight attention-grabbing topics like artificial intelligence, electric cars, and robotics, while the foundational materials enabling these systems develop quietly behind the scenes. Carbon-based wiring from KIST may be following a similar path. For now, it is under study in research centers and by aerospace and defense organizations. But the benefits, lighter weight, flexibility, and near-copper conductivity, are far too compelling to ignore. As manufacturing improves and costs drop, the transition from academic journals to real-world applications seems inevitable. If successful, tomorrow's motors in vehicles, planes, and heavy machinery may be built with carbon nanotube coils instead of copper. Such a shift could redefine efficiency, performance, and design possibilities across countless industries. Even sectors slow to embrace change would ultimately be drawn in as prices fall and the technology proves its value. Yet, the deeper meaning of this research extends beyond merely making a better wire. It challenges the very fundamentals of engineering. For over a century, metals have been our default conductors. Now, researchers are daring to ask, what if we moved beyond metals entirely? By pioneering carbon-based conductors, scientists are not only reimagining machines, but also charting new possibilities for lighter, smarter, and more adaptive systems. Though still under development, this innovation is already rewriting the design rules of electric motors. Future motors may not just be smaller and lighter. They could bend, flex, and adapt in ways unimaginable with rigid metallic predecessors. This marks the dawn of an era where nanotechnology and advanced materials lie at the heart of machines. History shows that breakthroughs in materials often trigger revolutions across industries. What began as a quiet experiment in a South Korean laboratory could, in time, become as ubiquitous as copper wiring is today. For those who marvel at innovations that append a century of engineering tradition, this story is only the beginning. The emergence of carbon nanotube-based motors reminds us that many of the most impactful technologies start humbly, out of the spotlight, until they suddenly reshape entire industries. Whether this invention completely replaces copper or settles into specialized niches, its promise is undeniable. The electric motors of tomorrow may not buzz with metallic coils, but instead pulse with carbon threads woven at the nanoscale, a true testament to human creativity and the boundless frontiers of material science.